In order to find the biconnected components of our graph, we're going to find the link components of it. This is the equivalence class of edges with respect to that link relation, which is two edges are linked if they're either the same or they belong to the same simple cycle. So in order to find these link components, we're going to use an auxiliary graph. So we're given some connected graph G, and let's say this is what our graph looks like. So we're given some undirected graph, and we want to, in that undirected graph, find all of the biconnected components. In order to find all biconnected components of this graph, we're going to find the link components. So our first step is to, on this graph, perform a depth first search. We're going to use this DFS in order to help us identify quickly the edges, which cycle edges belong to a simple cycle width. So given this graph, we perform a DFS on it. Let's say we start at this vertex. So this is the resulting depth first search traversal that we would find. So we have those discovery edges marked, and I've labeled the edges here as well. So this is our resulting DFS traversal. We start at this vertex, and then move to this one, and then this one, and then this one, and so forth. And we mark as back edges those instances where we're going back to an already visited vertex. So edges C, E, F, and J are back edges labeled by our depth first search. So given this graph now, this was our original graph G, we performed depth first search on it. Now we're going to use our labeling scheme that DFS marked edges as in order to compute an auxiliary graph. So this other graph B, this is just going to help us identify the link components of our original graph. Now this auxiliary graph is formed by, we have a vertex in this other graph B, where each vertex corresponds to an edge of our original graph. So this vertex A corresponds to edge A here, and vertex C corresponds to edge C here. Vertex E corresponds to edge E here. So this is how we define the vertices of this auxiliary graph. Then we connect them, we add an edge between vertices if this edge G and edge E have belong to a simple cycle together. So we're going to add edges in this auxiliary graph very specifically between those vertices which correspond to back edges in our original graph. So these are those vertices. So these are the only back edges in our original graph, C, F, E, and J. And remember that the existence of a back edge means that we have a cycle in our graph. So we're going to add an edge from this vertex to other vertices in this graph based on what cycle this back edge was a part of. So which edges we add, this is based on starting from edge C, which is a back edge. This formed a cycle with, if we were to just follow those discovery edges back, how did we get here in the first place? This was discovery edge B and discovery edge D. So we have an edge from C to B and C to D in our auxiliary graph. We have back edge E, which participated in a simple cycle with, again, just following these discovery edges back. It was in a cycle with G and B, and now we're back at the same vertex that E is pointing to. So in our auxiliary graph, E has an edge to G and B because they participate in a cycle together. Back edge F forms a simple cycle with, if we just follow those discovery edges, how we encountered them. So how we got to this vertex was through this discovery edge G. How we got to this vertex was through discovery edge B, and how we got here was through discovery edge D. And now we're back at the same vertex that our back edge F is pointing to. So in this auxiliary graph, F has an edge to G, B, and D. So these are those edges to G, B, and D. And lastly, for back edge J, this forms a cycle with discovery edges I and H. So in our auxiliary graph, J has an edge to I and H. So notice that we don't add an edge between two vertices in B, which correspond to discovery edges in G. We only add edges from back edges from G to other vertices which represent discovery edges. So this is that relation to find. For every back edge, we add an edge from that, let's call it a back vertex in B, to discovery vertices based on if they form a cycle. Okay, now notice that once we have this auxiliary graph, we just have to find in this auxiliary graph the connected components, and those connected components of this auxiliary graph are the link components of our original graph. So this is why we move to our auxiliary graph. So what is a connected component in B? This is just, we've got here a connected component, just visually we can identify these, but algorithmically we can use then either breadth first search or depth first search. So these are our connected components. Why are they connected? That means that every pair of vertices in this auxiliary graph has a path between them. So for example, C to G. Here I have a path to get from C to G, which means in our original graph that edge C formed a simple cycle with edge D. Edge D formed a simple cycle with edge F, which formed a simple cycle with edge G. And by our transitivity property, that means that edge C formed a simple cycle with edge G, which means these two vertices in B, as edges in G, they formed a cycle, belong to the same cycle, which means that those belong to the same biconnected component. So the connected components of this auxiliary graph are the link components of our original graph. So this is the main idea. We are given some graph, which is an undirected graph. So this is our graph G. It has, let's say, n vertices and m edges. On that graph, we perform depth first search. Really, it must be depth first search here because we're going to use the resulting depth first search in order to find for every back edge a cycle. So we're able to do that repeatedly, efficiently with depth first search. So running depth first search is big O of however many vertices and edges are in our graph that we're running it on. Then we compute our auxiliary graph. Now this auxiliary graph has one vertex for every edge of our original graph. So that means we've got m vertices. And I'm going to talk in a moment about how many edges are here, but for now let's just say there are L edges, and we'll figure out exactly how many in a moment. So in order to build this, we have to add every vertex and edge of this auxiliary graph B. So this will be however many vertices plus however many edges we've got in that graph. And then in this auxiliary graph, we find the connected components. So we can find connected components using DFS or BFS, and this will output, we can find here's one connected component, here's another one, and here's another one. So no matter which of those traversals we use, this will be have a running time linear with respect to however many items we had. So we've got, in this case, this many vertices and this many edges in that auxiliary graph. And then for every connected component of our auxiliary graph, we're going to output those vertices. So we identify this as being in the first connected component. These are all in the second connected component. And these are all in the third connected component. So we'll output all of the vertices of B corresponding to each connected component of B, and those correspond to edges of G that belong to the same link component. So I've got here a connected component, here our second connected component, and here our third connected component, which means in our original graph we had this was one link component, this single edge, which is one biconnected component as well. This induces one biconnected component. Here we have our second link component. The edges that this link component induces forms a maximum biconnected subgraph. And our third link component consists of these edges, and those edges induce our third biconnected component. So we have, since we're outputting vertices of B, we have exactly m vertices of B to work with. So our total running time here is, since we're doing each of these actions consecutively, this is just a sum of each of these. So this is big O of n plus m plus L. However, this is big O of n times m, and the reason for this is because the number of edges that we have in this auxiliary graph could be large. This is exactly because L could be as large as n times m, and then this becomes our dominant term. In fact, we could have big O of m back edges in our original graph. These correspond to vertices in our auxiliary graph. And each of those back edges can participate in a cycle that has big O of n edges. So we have each of these back edges is on a cycle where that cycle has, since this is a simple cycle, we're not repeating any vertices, at most big O of n edges associated with it. In that case, we have to add a lot of edges to our auxiliary graph, because we only add an edge to our auxiliary graph if this back edge formed a simple cycle with these discovery edges. So if we've got big O of m back edges, and it could be on a simple cycle with big O of n discovery edges, then we would add in our auxiliary graph an edge from this back edge to each of those discovery edges. So we could have a lot of edges in our auxiliary graph. So this is how we got our total runtime. Notice that the bottleneck of this algorithm is L. This is the number of edges that we have in our auxiliary graph. And we can do even better than this if we're more careful about how we construct our auxiliary graph. We only need edges there in order to help us compute the connected components. So what you'll see in the next video is how we can do this more efficiently by instead carefully constructing this auxiliary graph, this proxy graph, so that we only add the least number of edges possible in order to maintain connectivity in B.